So in this section, we're going to start by talking a little bit about the history of exploring animal intelligence. Now, this really goes back to theories of evolution. When Charles Darwin presented his work on the origin of species, including his postulates about natural selection and the modification of organisms over time, this really hit with a lot of people. This got a lot of attention, but he purposely kind of pulled away from talking about human evolution. This was mostly about animals, non-human animals. But really, to bring his theory together, he knew he had to connect other animals to humans. And what was really characteristic about humans that differed us from other animals is we were highly intelligent. So he was starting to think about the connection in intelligence between humans and non-human animals. So Darwin was looking for what he called mental continuity. In other words, the connection between the mental abilities of humans, our ability to reason and think and solve problems, with that of non-human animals, to show that relationship. And he wrote a book, very famous book that came after Origin of the Species, called The Descent of Man, where he really tried to explore the mental life and evolution of animals and their thought processes. And one of his young associates, a friend of his, a guy named George Romanes, he asked him to start collecting stories about animals having qualities in their thinking that was similar to humans. We call this time an anecdotalist time because an anecdote is stories. So the first attempt to try to understand animal intelligence was just to put together a collection of stories, to look for homologous features. Now, Darwin talked a lot about homologous features of structure, right? So the forearm, for example, of humans, the radius, the ulnus, and the humerus, bats have them, lions have them. They are just slightly different. Even whales have phalanges, radius, ulna, and humerus. And he said, okay, we have these similar underlying structures that shows common ancestor. So we need to find homologous mental processes. If humans think and solve problems and have these mental characteristics, we should try to find them in animals. So here's Charles Darwin's The Descent of Man, where he was really trying to explore those mental continuities. And Romanes started asking people he said were of high standings, and this is things like the clergy and teachers, and to find and collect stories, anecdotes, about animal intelligence. And he wrote a book called Animal Intelligence in 1988. And I've read part of this book. It was really interesting. You know, he tells stories. He tells stories about ants, for example. There were the black ants and there were the red ants. And the black ants and the red ants had racial bias against each other. Oh, a human characteristic. And they had wars against each other. Oh, humans do that. And he even tells the story that he collected about ants fighting other ants. And one ant was not fighting, not holding up its end. He was a coward ant. And at the end of the battle, the hero ants went to the coward ant and killed him and buried him in, and I quote, a shallow grave because of his cowardice, right? That's very human-like. This is called anthropomorphism. That's a big word, anthropomorphism. So morph means shape of, and anthro is humans. In other words, we ascribe human characteristics to animals. And there's lots and lots of stories in this book about animals lying and being deceitful and solving problems and contemplating. just from people's stories that they sent to him. And so this anthropomorphism isn't really getting us very far in research. I mean, sure, it's a good start. This is the 1800s, looking for that mental continuity. Find animals that show human-like thinking. That's homologous, right? It's an attempt. Kind of gets in our way, and it's a real problem, actually, even in research today, where we assume human characteristic in animals. Animals think like humans. They have consciousness like humans. They have sense of self like humans. And that really does a disservice to the research, but also to animals. Animals have their own mental lives. I remember watching this video of people seeing in an aquarium two otters holding hands. So isn't that cute? They're holding hands, and you can hear people in the background talking about how cute the animals are and how much they must be in love with each other, and they're the best friends and they love each other, really human characteristics. Turns out that otters like this hold hands in the wild all the time. Why? It helps them float. It's not the way they hold hands the way we hold hands, although there might be some connection and affection, but it serves a purpose, right? I mean, sure, we do this all the time. I do this with my own pets, right? I think about what my cats are thinking, and I even say it in their voice, or my dog, and how my dog loves to play, and how he loves me, and all this stuff like this. And that's fine day to day, but it really doesn't help us in research and theory to ascribe these human characteristics to animals. It gets in the way of really trying to understand the mental lives of animals and how they learn and their memory and their decision making. And we need to really try to avoid anthropomorphizing our animals in theory building and research. So a guy named C. Lloyd Morgan, he was a British ethologist. Remember, ethology is the study of animals, usually in a biology department, usually thinking about natural behaviors. But he was also a psychologist. And he's best known for what was called emergent evolution ideas, which is his theory, and it gained some traction, that during the course of evolution, sometimes something emerges, something new that is greater than the sum of the parts. In other words, the example often given is consciousness. Suddenly, because of the nervous system of human beings, it was so complex and consciousness emerged, right? Now, Morgan tells a really great story, and I love this story. It's one of the most famous stories in animal behavior. It's the story of his dog, Tony. There's a picture of it. I found this in a book. There's Tony the dog. And here's how the story goes to try to illustrate a point. So every day when C. Lloyd Morgan would leave his house, he would go through this gate, and his dog would run right back and forth, trying to get out to him, right? Wanting to be with him, as dogs do. And he would run over here, and he'd run over there, and he'd stick his head in, and he'd bark and yell and bark and run back and forth, back and forth. And one day, by chance, Tony stuck his head right in this spot, and when he pulled his head back, he accidentally unlatched the gate, and it opened up. And out Tony went. And Tony escaped. How interesting. The next day, Morgan leaves, and Tony runs back and forth and back and forth and back and forth and back and forth, and eventually sticks his head all over the place, and then maybe not the next day, but a couple days later, he catches the latch right here, opens up the gate, and out he runs. He's so happy. Well, day after day, Morgan noticed that Tony stopped putting its head over here and over here, over here, or over here, and just kind of stuck his head in these spots over here and would get out more and more frequently and quicker. Until after weeks and weeks, Morgan would leave and Tony would run, stick his head right in that spot, lift up the latch, and out he would go immediately. And as C. Lloyd Morgan tells the story, one day Tony gets out just like he can, and a passerby says to C. Lloyd Morgan, "Wow, that is one smart dog. He understands how a latch works." And Morgan thought to himself, no, you didn't see what just happened. You didn't see what took months and months, because if that dog understood how a latch worked, he wouldn't have moved back and forth and learned slowly. We call this trial and error learning, meaning keep trying a bunch of stuff, making a lot of errors, and then something happens to work, and those behaviors tend to persist, the ones that tend to work. In other words, sticking your head around here and not over here and not down over here. And through a very slow process of this trial and error learning, eventually Tony got out. But it doesn't mean he understood how the latch worked. He didn't contemplate, I see how everything worked. It's just stopping behaviors that tend not to be associated with getting out and continue behaviors that tend to be. And the passerby only saw the byproduct, only saw the end, and said, this is a thinking animal, as opposed to just behaviors being modified. So what we have to start with to understand this, which makes this story, is what's called the principle of parsimony. Parsimony means at the simplest nature of. One should always choose the simplest explanation of a phenomenon, the one that requires the fewest leaps of logic. So when it comes to Tony, a leap in logic is this animal is understanding the mechanisms of a latch. He understands if he lifts the latch, he may leave. That's a really complex assumption, that he understands all of the complexity of lifting up a latch and how latches work. A simple explanation is he stopped doing behaviors that weren't working, and he tended to do behaviors that were associated with getting that reward. So, sticking his head over here, this behavior over here was never rewarded, so he tended not to do that. And he tended not to do this and this and this, and he just kind of poked his head around here. This took weeks to do. And it was just through trial and error, very simply, he tended to persist in behaviors that were associated with reward. That's the principle of parsimony. The principle of parsimony is very similar to this rule that we use in everything from astrophysics to chemistry to biology, which is Occam's razor. One should not increase beyond what is necessary the number of entities required to explain anything. In other words, don't add complexity. Don't assume the most complex explanation when a simpler explanation is going to help you explain it. So Morgan took this idea, the principle of parsimony, to be parsimonious in our explanation, and wrote something very directly related to animal behavior. This is known as Morgan's canon. And here it goes. In no case may we interpret an action as the outcome of the exercise of higher psychical faculty. In other words, higher mental capabilities, thinking, reasoning, complexity, consciousness, if it can be interpreted as the outcome of the exercise of one which stands lower in the psychological scale. Simply trial and error learning and just repeat behaviors that have good outcomes, and tend to not repeat behaviors that don't have good outcomes. You don't need reasoning for that. You don't need higher processes for that. A simple nervous system, a simple insect nervous system, a slug nervous system could handle these simple processes of continuing behaviors that have good outcomes and don't continue behaviors that have bad outcomes or no outcome. And this idea is extremely important when we think about motives for behavior and how we understand behavior. And what we're going to try really hard to do is always start with the most parsimonious explanation. We're going to keep coming back to Morgan's canon. Can we explain this behavior without having an animal that contemplates, reasons, solves problems in its head before doing them? Things that humans can do, but aren't demonstrated easily in non-human animals. When we fail to do that, to explain it with simple, then move up, then go to a more complex thing, and we will. We will talk about more complex assumptions, especially when we start looking at other apes and cetaceans like dolphins and whales. We can't explain them through these trial and error simple processes. We need to move up, but we're not going to do that at the start. We're going to start with the most parsimonious interpretation, following Morgan's canon interpretation of animal behavior. So now we talked a lot about classical conditioning in the last section. Now we're talking about instrumental conditioning. Instrumental conditioning, as we'll find out, is very similar to operant conditioning, another term that B.F. Skinner used. There are some fundamental differences in the theory of explaining the behavior, but the behavior itself is very similar. So we talk about instrumental conditioning because behaviors that occur because it was previously instrumental in producing certain consequences, certain outcomes. Unlike classical conditioning, there's a contingency between the behavior and the reinforcement or biologically relevant reinforcement. Okay, so back to Pavlov. Remember Pavlov? Ring a bell, give the dog food. Ring a bell, give the dog food. The dog doesn't have to do anything to get the food or to hear the bell. We just simply pair them. Or in auto shaping, key light comes on, food drops in the hopper. Key light comes on, food drops in the hopper. The bird did not have to peck the key light in order to get the food. In other words, there's no contingency between the behavior and the outcome. This is not true in instrumental conditioning. The contingency between the behavior and the outcome is really important, and we're going to have a whole lecture on just those contingencies. So let's say I'm trying to teach a dog to sit. So here's a little dog. It's not the kind of dog I have. That's a nice picture I found on the internet. But that's a pretty dog. What is that, like a pug? Anyway, so I tell the little dog, I say, okay, sit. And the dog just looks at me, doesn't do a thing. So there's no reward, there's no outcome. I'm not going to punish him. I'm just not going to do anything. And I'm going to say, sit, and the animal doesn't do anything. I'll say, sit, and the animal doesn't do anything. But by chance, occasionally, if I say the word sit and the animal sits, I'm going to give it some food because it did the behavior I want. The behavior that we're looking to change, the behavior we want to modify, we call that the target response. We'll come back to that term, target response. So, sit, nothing. No food, no snacks, no reward. Sit, nothing. Sit. Oh, sit. As soon as I see the target behavior, he gets a little doggy bone. Maybe I praise him. Who's my good dog? Who's my boy? And we just do that over and over. When I present the stimulus of saying the word sit, and it sits, it gets food. No sit, no food. There's that contingency. Doesn't take long before the animal hears the word and sits. And the person that really is best known for theories of instrumental conditioning is Edward Thorndike. We're going to talk a lot about Thorndike in this section. We're going to talk about Thorndike's theory and whether experiments support or fail to support his theory. So he's an American psychologist. He was a graduate student at Harvard, and he actually worked with William James, the very famous father of psychology, William James. And he was an animal behaviorist, interested in animal behavior, ethologist, but also a psychologist. And he spent actually his career, very long career, working at a teaching college at Columbia University. And his main role throughout his career was teaching teachers how to teach. Really modified and changed the modern educational system, K through 12. A lot of what's done today in classrooms have their root in Thorndike's theories of teaching and learning. But that's not how he started. He started really looking at animal behavior and animal learning, and then applied what he learned from animals to children. So here's the story. It's kind of a nice story. So Thorndike listened to a talk by C. Lloyd Morgan and heard the story of Tony the dog, and the problem with anecdotalism and the problem with anthropomorphizing animal behavior. And this really hit home to Thorndike. He's like, yes, this is a problem. We're not understanding learning by telling stories about racist ants. This isn't helping. And he simply said, I just want to do what Morgan did with his dog Tony, the story of Tony. I'm just going to do it in a lab. So here's what his idea was. He just set up a Tony experiment with cats. He made these puzzle boxes. These are called puzzle boxes. And in the puzzle box, if the cat hit this lever, he called this a manipulandrum because it could be manipulated. And he stepped on this, then the door would open and he would go out and he would get some fish. And the puzzle boxes, there's been lots of drawings of these puzzle boxes. And this is the lore of early psychology. Turns out that Thorndike was an excellent theorist and researcher, but he really kind of sucked as a carpenter. These are actual pictures of his puzzle boxes. They're not the best pictures, but he basically just slapped these things together. But the idea was create a situation where the animal has to do a behavior to get a good outcome. The behavior was step on this. And then simply time. Time is our record of performance, our change. So here is the cat. The cat is in the box on the very first trial. And the cat's just walking around, meow, meow, walking around inside the box, sticking its nose all over the place, trying to get out, putting out its paw. But he's trying a lot of different behaviors. He's just active. He wants to get out and he wants to get some food. So he's just walking around randomly. And it takes a while. And then by chance, he happens to hit the manipulandrum. Just happens to hit the lever by chance. And out he goes. And he goes and he has himself a little snack. And then after a while, puts him back in the box. And does the cat go right back, just to go right back and start pressing the lever? Oh, yeah, I understand how this whole system works. I press this lever, and it pulls this string, and it lifts this box, this door, and out I go. I totally get it. I learned one trial, only took one trial. No, the animal, when it's put back in the box, walks around randomly, blah, 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 just trying to get out, sticks its paw through, meows, meows, and gets out. But this time it didn't take him over 360 seconds. It took him only a couple minutes. And then we put him back in. And this time, he doesn't go and press the lever. He walks around, meow, meow. But the key is that he really, after a while, isn't really walking over here and sticking his paw through here, because that hasn't been connected or associated with getting out. And over here, he tends to be around here a little bit more. And by chance, he gets out. This time it took him 250 seconds. Trial after trial, he just gets a little faster and a little faster. This is 2 minutes right here. He's still taking 2 minutes after almost, 15 trials? If the cat understood how the whole mechanism worked, he'd go over and I want out. I'm hungry. I'm going to go slap on the little lever and out I go. But what you can see is trial after trial, we get what's called an acquisition function. It learns and it gets faster and faster. Still, we're all the way up here in the 35th trial. It's still walking around. Doesn't just go and press the lever out. It's still just walking around. But he's not walking over here. He's not walking over there. He's kind of playing around here and sniffing this thing and playing with it and sniffing it. And then by chance, he hits it hard enough to where out he goes. Now, he's been doing this 60 trials. Now he gets in there. He wants out. He wants to go get some snacks. He just goes over and hits the lever. Just like Tony the dog. After days, Tony eventually just went over the latch and lifted up. And the passerby goes, wow, he really understands this whole mechanism. No, you didn't see the fact that it took him a lot of trial and error, and eventually they get better and better. They modify. This is an acquisition function. Okay, here's my best animation of it. Forgive me on this, but this is kind of fun. So here he is. He's walking around. He's just walking all over the place. He happened to hit it just by chance. Out he goes, and he has himself a little snack. And then maybe we wait a little while, and then we can put him back to try again. So we put him back, close the door, and he doesn't go right over to the lever. He walks around and up and out he goes. But it took him a little less time because he didn't spend time over here. He spent a little bit more time in this area. Stop doing the behaviors that aren't connected with getting out and do more of the behaviors that are, which are over here. Trial after trial, 40 trials, 50 trials of sticking the animal in this box. Eventually he goes right over there, presses the lever, and out he goes. But that took a long time. Trial and error. If the animal reasoned, understood the whole concept of pressing a lever to manipulate this thing, which lifts a string, all that, he would have gone out right away. If you were in there, if you were the cat, you're a human being and you're stuck in this box, and there's money outside here, and every time you get out of the box, you get money, you might walk around a bit, try different things. But as soon as you hit that lever, you're like, I totally get it. I totally understand. Next trial, or maybe it took 2, who knows? You go over and you just press the button, out you go. But animals have to go through these trial and error learning. Slow process of learning, of getting faster and faster. But it isn't just, I see how it works now. It takes me 2 seconds. So here's some terminology that we're going to use a lot for this section. So the first stimulus, we call this the discriminating stimulus. Depending on the book, if you have a book, sometimes that's referred to as S sub D, the discriminating stimulus. I use S1 because it's the first one. It's the first stimulus. The initiating stimulus, sometimes it's called. So, in our trying to teach a dog how to sit, the word sit is the first stimulus. If I want them to do something else, I would say a different word. Then we have R1, response, the first response. We often call that the target response. With our little pug dog, the target response is sitting. With the cat, the target response is hitting the manipulandrum and leaving. Maybe I want to teach a dog to roll over. Roll over is the target response. Maybe I want a child to have better behavior in class. I want to modify that. So I say, okay, I want the child to be able to sit for 10 minutes and look at a book. Target response. It's the one we're trying to change. Then we have S2. S1, S2. It's the second stimulus after the target response. We can call that a reinforcement. Sometimes a reinforcement, the common way of thinking of reinforcement is something good. I'm reinforcing you. That's great. Sometimes in psychology, we use reinforcement as just a stimulus. It can be bad. It can be a bad thing. Yell at the animal or shock or something. But I'm just going to talk about that as S2. Depending on the book, sometimes a book might call this the stimulus O. also referred to as O, as the outcome stimulus. So keep that in mind. I prefer S1, R1, S2. It makes things easier because S stands for stimulus. When we talk about reinforcements, we're going to use two words, appetitive and aversive. Appetitive comes from the word appetite, and I just want you to know it as something the animal likes, something good. It might be playing with the ball. It might be a delicious snack. It might be praise, rub their belly, whatever. It's something that the animal would really like to have. Aversive is something it doesn't want to have, aversive stimulus. This might be a shock, or maybe you yell at the animal or something, right? We'll talk about aversive stimuli when we talk about punishment. Finally, we need to think about the R2, which is any natural response to the reinforcing stimulus. This is Pavlovian. This is the stuff we've talked about. If this is food, what's a natural response to food? A natural response to food is salivation. A natural response to food might be emotional. A response might be, ooh, I feel good. What's the natural innate? This would be like the US and the UR in Pavlovian talk. Okay, so what's the S1? S1 can be rather complex. It might not be something really simple like sit, roll over, lay down. It might be something like an environment. When the animal's in this environment, the stimulus, the S1, might be the environment and it might be the site of this manipulandrum. What's the R1? R1 is pressing the lever. It's a response. It's an action, pressing the lever. What's the S2? What does it get if it presses the lever? It gets out, which it wants to be out, and it gets to eat some fish. So S2 could be being just outside of the box, but let's make it easy. S2 is the delicious fish snack. S1, the manipulandum. R1, pressing it. S2, get out and get some fish. And what's the natural response to fish? What's the R2? It's feeling good. Emotional, feel good. Salivation, digestive system. The R2 will come into play in another lecture, so we should just talk about it. So in the next lecture, we're going to talk theory.